So we're going to be talking about polynomials, essentially the majority, the first half, and then some logs and exponential functions in week 8. So it's all about polynomials. We're going to examine rational functions, basically polynomial over a polynomial, do some long division of polynomials, and more about exponential and logs. So a lot to cover. So previously, we left off, if you remember, we were talking about essentially polynomials, which is basically just a function, and we can add, subtract, multiply polynomials just like any other functions. Each of these operations results again in a polynomial. So it's just essentially a type of function. So let's look at some examples. So let's add these two polynomials, P and Q, they're polynomials. Let's add them together and see what happens. So what do we do if we add these? I'll just write it out quickly. So negative 3x to the power 4 plus x minus 2. What is the answer? How do we add them? Well, yes? In the back?
Oh, it would be x to the 4.
Right.
Plus 3x.
Right.
Minus 7.
Yep. Perfect. And you notice what he did was he added the like terms. Again, add like terms. What about subtraction? And when you say adding, you can say the sum of two polynomials. When you say subtraction, it just means the difference of two polynomials. Don't get confused by the wording. So to subtract them, what do we do? Same idea. Subtract here. Anyone? You just put the minus inside. So 4 minus minus, this becomes a positive. So it's 7 x to the power 4. 2 subtract 1 would be plus x. Minus 5 subtract negative 2 be negative 3. Okay. So it makes sense. And you see that the power here is a 4 and 4. What about multiplying two polynomials together? Ugh. Pardon? Yeah, it's so hard to tell who's talking because of the math. I don't see you, but I heard it from that area. Yes, I think it was you. It's going to be long, but then you're going to group like terms together. So let's do it together here. It is going to be long. So the first thing is you multiply, write it down, the question, and you sub it in. Okay, it is going to be very long. Now we take the first term and multiply it by everything in the second. So we take, let's use a different color. So this first term, multiply it by everything in here, and then in here, and in here. And then we move on to the second and multiply it and everything in the third. So you can see that there's going to be how many multiplications do we have to do? 9, right? Because there's 3 times 3, that's 9. So let's do the first one. So 4x to the power 4 times negative 3x to the power 4, that's going to be negative 12. Now, how do you multiply like these exponents together? Ugh. Do we remember before reading week the rules of exponents? Right, you add them, perfect. So it's 4 and 4. So we add them. So this is an 8. Next one, 4x to the power 4 times x is going to be 4x to the power 5. The next one, 4 times -2. So that's going to be 8, and then it's just x to the power 4. I'm just going to write it on the next line. I could write one, actually, I could, just so I see a pattern. So then we move on to the 2x. So the 2x times -3x to the power 4. That's perfect. Plus 2x squared plus, yep, continue. Mine. Right. And then we move on to the last one is plus. Right, perfect. Good. Okay, so now we have that. We can group the like terms together. So we're not completely done, right? We see there's a negative 12x to the power 8. That's the only one. But so we could kind of cross that off if we wanted to. I'll cross this off. Now, what else could we group together? Yeah, which would leave us negative 2x to the power 5. And it's kind of, I wrote it this way because there's a diagonal pattern. A little bit. The next one. Yeah, the 4s. 15 subtract 8 is 7, x to the power 4. Next one would be 2x squared. Subtract 9x plus 10. You can write it this way. You could also write it, if you really wish, the other way around with the 10 first. It doesn't matter. Just write it out. Oh, okay. So what did we notice? What is the largest power in part A? What is the degree of the sum of P plus Q? Sorry. So it's 4. So the largest powers here, this one's 4, and this one here is 8. Just highlighting them for the next question. So the degree of the sum for the first one was just 4. The degree of the difference here was 4. And the degree here was 8. It happened to be. Didn't have to be, but it happened. So like these degrees determine how large basically the polynomials are. It can be useful kind of like in computer science if you're trying to do some modeling. And it just gives you an idea or a general rule without doing the work of what can happen or how big this polynomial is. So sometimes it's just useful to understand the degree and look at it without looking at every little part to find the order, another word for degree, used in computer science of how large these expressions or these polynomials can get. So I was going to write this all out, but to save time, I just printed it for you. So let P have degree M and Q have degree N. And suppose M is greater than or equal to N. Then the degree of the sum is at most M, at most, doesn't mean it has to actually be M. And the degree of the difference is at most M, of the largest one. Now the degree of P times Q is at most M plus N, which we kind of just previously saw. Since the degree of P is at most M, we see that it has a term with x to the power M in it. It's going to have that term. Since the degree of Q is N, it's going to have a term in it with x to the power N. Then when we form the product, multiply P times Q, we obtain a term arising from the product of the highest power terms, namely this x to the power M times x to the power N. And it can, of course, have a coefficient in front. Since x to the power N times x to the power N is equal, we just add those by the rule of exponents here. We just add those exponents together. So it's x to the power M plus N. So the highest power term is in P times Q has this power M times N, meaning that the degree of P times Q is M plus N, which is kind of what we just did in the previous example. This is just kind of an understanding of what we do. It's actually quite interesting because you can obtain a great deal of just knowledge by solving like first year math questions in a math course. This is actually, it can be used in other areas. It's like a little mini proof, but the idea is back to this example. You can add polynomials, you can subtract them, multiply them together. And I posted this all online. Now, zeros and factorization of polynomials. Suppose you have a number t, and this is called a zero or a root. So the textbook actually, a lot of textbooks use either the word zero or a root, but I'm going to use it interchangeably, either zero or root. So please know these words. To note the function f, if at this variable t, so t is just a variable, it's equal to 0. So we want to find the zeros of this function. So this basically means, so we set this to 0, the function, we set it to 0, and we solve for the variable, this t, or it could be an x, whatever the variable is. So let's do that. Now there's ways to do this. So we want, let me write this down, to find an x, let's say, such that x squared minus 6x minus 7 is equal to 0. So we want to basically solve this x squared minus 6x minus 7 equals 0 for our x. So there's different ways we can do this, right? We've learned this before. You can complete the square. You could try the quadratic formula. I'm going to factor it from high school. So let's factor, because it's just easier for this particular question. So this implies x, I put the x first. So have to have a 7 here and a 1. So this would have to be negative and this would have to be positive. And you can multiply them out to check your answer. This is from high school factoring. So therefore, we see that when x is equal to 7, this is going to, the left-hand side will be 0. Another root will be when x is equal to -1. So these are going to be the roots or the zeros. Of f of x. So it's just basically, again, it's just solving. So if quadratic formula is easy for you, you can use that. If factoring is easy and it works out. You should know how to factor from. Everyone know how to factor? Yes? X plus 1 here. So I kind of see like these numbers are kind of straightforward and simple. So I put x here and x here, and then I see 7, like what are the factors of 7? So basically 7 and 1, right? Like, because it's 7 is prime. So I have to put 7 here and 1 here. Then I have to think about, like, is this going to be plus or minus here? Because there's a minus here. This is going to have to be minus, because a -6 is here. So what factor gives us -6? If you multiply it out and use FOIL to check. So I see that it's going to have to be a minus here and a plus here. It's sort of like a game, but if anyone likes video games or whatever, figuring out if it's going to be a minus or plus. And I just kind of work it out, the different combinations in my head, and then I write which ones would work. So that's something you should know from high school, though. Or you could use the quadratic formula or completing the square. Okay, so those are the roots, because you see if x equals 7, 7 minus 7, that's 0, so -1. So those are the roots. So what do the zeros or the roots of a function represent geometrically? So let's write a little note. So the zeros, anyone know? Or roots? What do these mean? Okay, of, say, a function. So they're basically the x values of the points where the graph of the function intersects the x-axis. So it's the y values are the 0 points, are as basically 0 at these points. So basically this means that it's basically where this graph intersects that x-axis. So you have, and the next example shows it a little bit more clearly, but it's where that, crosses the x-axis or intersects it at some point. So let's look at this example. What is just the graph of x squared? Well, x squared is, we learned this before. This is x squared, right? What about x squared plus 2? Let's just draw a little sketch. We know it's up here, right? We just move it up. So it's going to look like this. Pardon? So yes, find the zeros of this graph. You can't, right? Because it doesn't intersect the x-axis. This one does, right here at 0, but this one does not. So we can therefore observe just simply by like drawing a sketch. That the graph of this particular function, it does not intersect the x-axis, as we see. So there's no zeros. Or roots, whatever you wish to say. So another way of phrasing this and seeing this is if you wish to use the quadratic formula. So we could use the quadratic formula. And you would see that if we say f of x equals 0, you see that this has no solution. And you notice this, why? Because you cannot factor this. You can't complete the square. And if you did use the quadratic formula, it will show you that there's no solution. So there's no solution to something like this if you try different ways. And you see it also in the picture, it does not intersect that x-axis, so therefore there's no solution. It just gives you that intuition of, because, and you think about the definition, this is when this f of x is equal to 0. Well, there's no, actually, I won't get into it. Don't want to confuse you. So the notion of a zero of a polynomial directly relates to the notion of a factor of a polynomial. So let px be a polynomial and t be a 0 or a root, then this x minus t is basically a factor of the polynomial, which means we can rewrite it in this particular way. We can have our this x minus t, this factor, times this g of x, where g of x is a different polynomial or another polynomial with basically a degree 1 less than the original polynomial p of x. So finding the zeros of a polynomial is just equivalent to finding the factors of that polynomial. So let's again see an example. So suppose we have like this polynomial, and it's on the next slide. Let's kind of like analyze it a little bit. So give examples for factors of this polynomial. So we have a polynomial. So when p of, let's say, 4. Well, when x equals 4, 4 minus 4 is 0. So this is going to be equal to 0. We know this. So this implies, therefore, 4 is a 0. Of p of x, which implies, therefore, x minus 4 is a factor. Also, let's look at when x equals -3. Well, -3 plus 3, this is 0. So this whole thing is 0, which implies, therefore, -3 is a 0 of p of x, which therefore also implies that x minus -3, which is equal to just basically x plus 3, this is also a factor. So for part B, so x minus 4 and x plus 3, there are factors already. But what about this other x squared plus 5? Well, x squared plus 5 cannot be factored any further. And this is because x squared plus 5, there's no way this can be equal to 0, because then it would be you move the 5 to the other side. So x squared would have to be equal to -5, and then take the square root. You can't take the square root of a negative number. So you can't do this, which we've learned before. So find the zeros of this. Well, we already did it. So the 0 here would be obviously 4, and the other 0 is -3. So those are the zeros. Now I'm just going to go back. So basically, this was a factor. This was a factor. Just to repeat it, this is not a factor. And it cannot be factorized. What else to say? If you multiplied it all out, what would happen? So if you multiply the terms out for this p of x, and what would you think the degree would be? Anyone? So if we multiply it all out, all the terms, like, what do you think the degree is? Almost. So x, so you look at the highest one, there's x here, and x squared here. So multiplying that all out. The highest power is the degree. We would see that it would be 4. Oh, you can see that. You just multiply it all out, and you can check this yourself. I won't check it all for you, but because you have x squared, x here, and x. So how many zeros can a polynomial p have if the degree of p is equal to n? I'll just write a little side note here. So if a polynomial let's say p has degree n, then of course we learned then p has at most n factors. So consequently, p has at most n zeros. So we noticed something from the definition. Of a zero. That a zero corresponds to a factor in a polynomial. And vice versa. So there's a related. So it's just like a little side note. Okay, so if I give you basically an easy function, then it's easy to kind of understand what happens. But if I give you a difficult function, then it's like things can be difficult. So it really kind of depends on the functions to find like these zeros. And so what happens here? So an important fact about polynomials is basically that they're continuous functions. So what does discontinuous mean, or not continuous? So suppose we have a graph like this, and we have a hole in it. Or we have, and then it continues, and then we have a jump. So we have a jump, we have some holes here, whatever, like this, a picture. So basically like this picture of something, a function with some holes or some jumps. So this function, or basically graph, let's say, whatever, it's not continuous. This is an example, not continuous. So therefore, this graph cannot belong to a polynomial. Why? Because polynomials are continuous. So what is continuous? So basically, something like this basically has no jumps or holes. In the graph. So that would be an example of a continuous graph here. So how I like to think of it, imagine you put your pen on a piece of paper and you draw a line and you don't raise that from the paper. So this is continuous. If I lift my pen from the paper, it's discontinuous. There's a jump or there's a hole or something. That would be discontinuous. If I keep my pen on the paper, that's continuous. The difference between the two. So we're going to use this idea of what continuous is to help us figure out and approximate the value of a zero of a polynomial. Okay, so show that this polynomial has a zero between like these two values. Okay, well, suppose we're not sure what to do. We can start to plug in the values of x into this polynomial. So at -1/2, we plug it in and we compute this. So -1/2 cubed plus -1/2 squared, -1/2. And we just do some math here, arithmetic. And we can compute this, and this is 5/8, which is greater than 0. Let's compute the next point at 1/2. Same idea. So I'll just write this down. And you get -1/8, which is less than 0. Okay, so what does this tell you? So we could draw a little sketch at like 1/2 and -1/2. So at 1/2, we have like a negative value. And at -1/2, we have a positive value. Okay. But we know like polynomials, they're continuous, right? Like this is a polynomial and it's a continuous value. Oh. So it has to cross this axis somehow, has to cross some way. We don't know how, but it has to cross in some way. So it basically tells us that there is a 0 some way because it's continuous. There's no way to get from this high point to this low point with my pen without raising my pen and crossing that x-axis. It's sort of like there's a river and I have to cross to the other side some way. And how can I possibly do it, right? So I would have to go over a bridge, or, sorry, maybe that's not the best analogy, but so essentially, so since this P of -1/2 is greater than 0, and P is of 1/2 is less than 0. And we see, of course, this P of X is continuous. Because it's a polynomial. Then we see that there's a 0. Between like this -1/2 and 1/2. And you can see this by like drawing the picture. To get from this point to this point, you have to cross that x-axis. So we kind of conclude that there has to be a 0. And we can do the same idea for this question. We can work on it together. So P at 0.6, we can compute this. We just plug it in. And these numbers are a little harder, so I wouldn't. So this is less than 0. And at 1, well, 1 is the easier number. So this is obviously greater than 0. And you see that because since P at 0.6, this is less than 0, and P at 1 is greater than 0. And because this function is continuous, there's going to be a 0 between 0.6 and 1. So you see that there has to be like that point that crosses that x-axis. Because if one's up here and one's down here, and you can't just jump over the x-axis, then it would be discontinuous. Polynomials are continuous. And just repeating it, so hopefully you remember. So for like this, I'll leave this one for you. So this can be left as an exercise. And it's basically similar to the other questions. So you shouldn't have a problem. You just so you just will plug in the values essentially and compute it. So we have been sketching graphs for a while. We've done transformations, but when you sketch the graph of a function, you want your sketch to reveal just important behavior about the graph, essentially. So an important aspect thing to know about your function is what happens essentially when x gets very large. So when x approaches infinity, or when it gets very small, when x basically goes to -infinity. What happens to the y value is a question. So this can be easy to do when your function is basically a polynomial. We can do this. Now, I didn't want to write everything out because it takes a long time, but consider this polynomial, x to the power 3 plus x squared minus x. What happens and what can we determine about the behavior of this polynomial when x goes to infinity? Or essentially when x goes to negative infinity, there should be a negative here. Whoops. Anyways. So what can we determine? Well, if we plug in x values and you choose whatever x values you wish, but like a very like 1 million, or let's start with like 0, 1, -1, 100, -100, -1 million, +1 million. Choose very large values and see what you get. Well, if you do the math, you can see that as x gets essentially, what happens? Let's just analyze it without the stress of writing it all down. So as x goes to infinity, what happens to our y value? And this p of x is basically our y. What happens? We can see that this number gets large, right? This y goes to infinity, right? As like these values get very large. We can kind of see that. And it's dictated sort of by this first term, this x to the power 3. What happens when as x approaches or goes to negative infinity? What happens to our y value? Right, it goes to, well, the number gets to negative whatever, something, right? So it goes to negative infinity as we go in this direction versus this direction for like these values. Let me just highlight these numbers. So what is the dominating term here in the polynomial? Let's just like see the pattern. What is the important term? It's that x to the power 3, right? That dictates what happens to the polynomial, the behavior of the polynomial as x goes to infinity or x goes to negative infinity. It's that the largest term, essentially, the one with the highest power, the largest degree. The degree of the polynomial kind of dictates the behavior. So that's the point. I was going to write it all out, but I think you could probably compute all these yourselves. So the behavior of a polynomial when x goes to positive or negative infinity is basically completely determined by the behavior of the polynomial, the behavior of the highest power term of this polynomial. Let's just put a circle around it. So an example, so like this polynomial, x to the power 5 minus 7x to the power 4 plus 9, x to the power 3 minus 7, some zeros, whatever. So what is the behavior of this polynomial? So the behavior of this p of x is basically as x goes to positive or negative infinity, is determined by the behavior of x to the power 5. So as basically, let's say x goes to negative infinity, p of x goes to, well, it's going to go to negative infinity. Because like this is to the power x to the power 5. So it'd be like kind of sort of like negative infinity 5 times. Two of them are going to cancel and you're going to be left with 1 negative infinity, if that makes sense, because you're going to have negative, 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 negative. So some of the negatives will cancel and you're left with 1 negative. And as x goes to obviously positive infinity, p of x is going to go to infinity. Another example about the behavior of this, negative 3x to the power, let's say 7, plus 8, 9, 7, x to the power 5, plus 2x to the power 2, minus 71x. What is the behavior of this polynomial as x approaches positive or negative infinity? We see it's determined by, what is it determined by? Right, perfect. By of this highest power minus 3x to the power 7. Okay, so as s goes to negative infinity, what does this go to? Okay, when it goes, anyone? Because so it's negative. So there'll be 1 negative and then times the negative. So it'd be positive infinity. And when x goes to infinity, the function will be, this will be positive, but there's a negative here. So it'll go to negative infinity. Okay. One last example, and then we'll take a quick break. So we've seen this polynomial before. So let's just sketch it. So for the last 2 examples, previously, we saw that there's basically, so we know that basically p of x has a 0 between negative a half and a half, also a 0 between 0.6 and 1, and a 0 between, I'll just put dashes between -1 and -2. We know this from before. And we know, we previously did this, that p of x, it's always great to like write down what you know, even in physics or other subjects, as x goes to negative infinity. And p of x goes to infinity as x goes to infinity. So we can kind of draw this. Okay, so 1, 2. Don't have to be perfect. So as x goes to negative infinity, this goes down here. So it's in this direction. And as x goes in positive infinity, the function goes in this direction. Put some arrows on it just to kind of, so this is our p of x going to negative infinity. We know previously at 0, it was 0. So in this area between negative a half here and 1, or it has a 0 between, so this area. Between 0.6 and 1, it also has a 0. We could say here. And between -1 and -2, it has a 0. We can just say here. And we could say, okay, and we know the values were positive, negative, we could plot those points too. So then we could kind of connect the points without even really knowing all the details. And it could look something like that, essentially. So we don't know all the details, but we kind of know a few points. We know what happens at the endpoints-ish, or when this function approaches infinity, or x approaches infinity, or x approaches negative infinity. We can see how the function approaches if it goes to positive and negative infinity. And you can see that it between like these values, even though we don't know specifically where the zeros are, we can just kind of estimate there's between like these values, there are some zeros. I'll just take a quick break. So quotient functions, basically, this is a rational function. It's essentially just a polynomial. So divided by another polynomial. So don't overthink it. Obviously, the denominator cannot equal to 0. So when finding this domain of a rational function, we exclude the zeros of a polynomial in the denominator, like we normally do. So find the domain of like this rational function. So we have x squared minus 5x plus 6. It cannot, of course, equal to 0. So we could factor this out. We could say like this is 3 and 2, negative and a negative. And this would, if we apply FOIL, we're going to see that it's going to, the middle term will be negative 5x. We can find this. So this implies x equals 3 and x equals 2. And they are the zeros of the denominator. So the domain of Rx is basically R except for 2 and 3. So we could write it this way, like we did before. R subtract 2 and 3. Or we could write it as an interval like we did before. This is negative infinity, 2, let's say 3, all this area, all this area, all this area. So it goes from negative infinity to 2, union 2 to 3, union 3 to infinity. So this is nothing new. We've done this before. And these operations like addition, subtraction, multiplication, division, they work as basically the same way on rational functions, the same similarly to as how we did them on rational numbers. So nothing new there. Now, and it's the same idea too when adding rational functions. It's like we have to have, we multiply it and we have to have a common denominator, exactly the same as we did before. So kind of like get the idea of this common denominator. And then we could continue on. We just multiply the tops together. And we can do this trick because it's like multiplying it by essentially 1. Multiply like these tops together. And then it's all over a common denominator. So I won't expand it all out for you. But I'll just write it plus. Idea here is kind of like what we just did before. All over the same common denominator. The idea is now that we're using polynomials. So if you wish, you might want to basically simplify this. This expression. If needed. I won't simplify it, but it's the idea is what's important, because if you don't set it up first correctly, all the simplification in the world won't give you the right answer. But make sure that you understand and you have to have a common denominator. So that's with addition, and it's similarly with subtraction. What about multiplication? Well, in this case, it's pretty straightforward. We just multiply the tops because it's together. And the denominators together. So if you wish to simplify, you could, if needed. But I just want to make sure you remember to multiply the tops together, multiply the bottoms essentially together. If you have two, essentially like these like rational functions if you're multiplying two rational functions together. Which makes sense from before. So there, it's nothing new. We're just applying it to polynomials here. And then you could FOIL it or multiply it by each term if you wish. Okay. So sometimes when you have a rational number, you want to express it as an integer plus a fraction. Let's say something like 16/7. This is a rational number. And we wanted to sometimes express it like 2 plus 2/7, where this is an integer. And this is another rational number. And we know how to do this essentially for like these numbers. But how the same idea applies to basically rational functions as well. With polynomials, a polynomial divided by a polynomial. So without further ado, how to do essentially long division. Have we done this in high school? Long division with polynomials? Yes, anyone? Okay, so this might be a review for some. Don't worry essentially about the form. There's different ways of how to do it. We could write it this way if we wish. So we're going to basically write this as the sum of a polynomial g of x and a rational function of this particular form, where x squared plus x is on the bottom, and this is 1 power less than this part. I'm going to do it one way. You can do it your way. There's different forms, so don't worry. Like whatever gets you the right answer is fine with me. There's different methods, but I'll do it one way. So x to the power 5 plus 4x to the power 3 plus 5x to the power 2 plus 7. I'm going to write it over here. It's going to be divided by x to the power 2 plus 3. And I'm going to put the answer in this box. You can do it your way. So what number times this, and then we have to subtract them. So this is the numerator here, as you can see. This is the denominator. So if you choose x to the power 3, x to the power 3 times x to the power 2, that is x to the power 5. X to the power 3 times 3 is plus 3x to the power 3. It's good if you put them in the right columns to help organize yourself. Like don't put it over here or over here. Now, when we subtract these, this, you get a 0 here. I won't really write it. And 4 minus this is x to the power 3. Then you bring these down. So first, like learn the method of this. Okay. Now we have to choose a number when we subtract, when we multiply it by x to the power 2 and we subtract it, this first term kind of goes away. So what would be that number? Anyone? The next one? The x. So x times x to the power 2 is x to the power 3. X times this is plus 3x. Oops. I'll write it there. Then we subtract. So this becomes a 0. 5x subtract x, no x squared. This is brought down. This one is subtract negative 3x plus 7. Okay, so there's a 5x here that we want to get rid of, and there's an x squared. So we can multiply x squared by 5, and we would get rid of this, as we can see. Oops, running out of space. Five times 3 plus 15. You could write it over here if you wish to help see. So then we subtract these. This would be negative 3x. 7 minus 15 is negative 8. And we get this thing called like the remainder down here, essentially. So we're performing like long division. And our answer is over here. This is our g of x idea. I'll just make a few like little notes to the side. So we want to, so note that we want the degree of the numerator to be less than the degree of the denominator. Okay. So this is why we can stop here. So essentially, x to the power 5 plus 4x to the power 3 plus 5x to the power 2 plus 7 divided by x to the power 2 plus 3, it's equal to this x to the power 3 plus x plus 5 plus negative 3x minus 8 divided by what we just did, x squared plus 3. And we see we stopped here because the degree is less than the degree of the denominator. So we stop. So this is our g of x here. And this is kind of like our remainder part. I remember from high school, I used this notation like up here that I wrote in the corner. And then I have them in columns. So as an exercise, I'll leave this for you if you wish. You could write x to the power 6 plus 4x to the power 5 minus 3x to the power 4 plus 2x to the power 2 plus 7 divided by x to the power 2 minus 2 in this format of g to the x plus ax plus b divided by the denominator, x squared minus 2. So we could do that as an exercise, but if you wish, but I'll leave that for you. And this is the strategy of kind of how to do it. I just think it's best to work on some examples and go over an example if you wish. So let's move on. So just like with polynomials, we want to understand the behavior of a rational function when x gets very large or very small. So what happens essentially? So when it gets very large, meaning it's like essentially approaching infinity or like negative infinity, what happens? And you can always look at some graphs on, like, let's say Google, but let's continue. So the behavior of this rational function when x goes to positive or negative infinity, this is very similar to what we did with polynomials. And we remember this top was a polynomial, and this bottom was a polynomial of this rational function. So we can understand the behavior by like looking at the highest power of this rational function. So is the idea. So all you have to do is understand the behavior by looking at the highest power in p to the x and q to the x. Because you can like look at one polynomial, the top, the bottom, the polynomial on the denominator, and you can see which is the dominant kind of like polynomial in a way to say it. So what is the behavior of this polynomial? So to find like this behavior, if you notice on your assignment, there's a question of this polynomial. What do we do? So we only need to find the behavior of which? Find behavior of, essentially, let's color code it. You know, when I use colors, it's important of this over this. So if we simplify this, we get -5/3 x to the power 3. So this is what we have to like look at. So what happens as x goes to infinity? We see -5/3 x to the power 3 approaches, and this is the correct word. This will approach negative infinity, essentially. So the function so the given function approaches a negative infinity. And as x goes to negative infinity, we see that -5/3 x to the power 3 approaches positive infinity. So the given function approaches positive infinity. So we're just looking at like in the polynomial, in the numerator and the denominator, the highest power and analyzing that behavior. What about this one? Okay, so it's the same thing. So to find it, the behavior, this guy. We only need to find the behavior of basically negative 4x to the power 3 divided by 7x to the power 3. Let me just color code it. This and it's this. So we can simplify it. The x over 3 cancels and it's negative 4 over 7. There's no x in it. So this is essentially is a number. Because it has no x in it, obviously. So now what? Okay, so as x gets interesting, goes to infinity, negative 4 over 7, this is kind of obviously approaches, well, negative 4 over 7. So the function obviously goes to negative 4 over 7. Approaches, again, keep repeating the word, but it helps you learn it, right? So as x goes to negative infinity, we see that again, negative 4 over 7. I can just repeat what I just said. It's going to approaches negative 4 over 7, because again, it has no x in it. So given function approaches this negative 4 over 7. Okay. Yes?
Why not the x squared equals
No, like,
why not?
because it's the dominant term. Like there's a way to also see it. That would be something I could show you in the seminar for time constraints. But no, you just look at the dominant term because this doesn't factor into it. When the numbers get really large. And it's about approaching it. It doesn't mean it reaches it. So this is why it's skewed a little bit.
I just figured because the x squared would also be.
Yeah, it does. Right. Yeah, it does. No, that's not, because this actually goes to, no, that's not how you think of it. Yeah. And what about this? So this given this rational function approaches it approaches 0 as x goes to basically a positive infinity, because you see the denominator would get larger. And it also approaches 0 as x goes to negative infinity. I'll leave it as an exercise for you to basically do the relevant work. To actually obtain this answer on your own. We could do it in the seminar if you have any questions. Now, to draw like this last graph, or one of them, which graph was it? The second last graph, we saw that essentially, it's hard to draw, but it approached this -4/7. Let's just kind of draw -4/7. So this is -4/7. As it went to positive and negative infinity. You could check what this means, like you could use Google. But it went up like this, and then as x goes to infinity, positive infinity, it approaches -4/7. Don't worry about the details of like what happens around 0. And then as x goes to negative infinity, it looks something like this. So this both goes to basically -4/7 as basically x goes to infinity and x goes to negative infinity. This line is basically called, I'll use a different color, a horizontal asymptote. And suppose you use a grapher to graph it. It's tricky what happens like at all these little points, but it's just the general idea of what happens at infinity. So this is what I'm saying. So this line is called this horizontal asymptote. There's different types, like there's vertical asymptotes, etc. But we're only thinking about horizontal asymptotes for now. In general, a line is called an asymptote of a graph if the graph becomes and stays arbitrarily close to that line when x gets very large or when x gets very small. Okay. So arbitrarily close it just means it approaches it. It doesn't have to reach it. It's sort of like the intuition is a limit, like it's getting closer and closer and closer. Like let's say I'm walking towards someone and someone's over there, but we're walking at the same one step every like second. So I never actually reach that person, but I keep getting closer to that person. It's a bizarre notion. So to investigate, so the strategy to find this horizontal asymptote is if there exists one of a rational function, we only need to investigate the behavior of the function as x approaches infinity and x approaches negative infinity. If the behavior of that function is approaching a constant number, let's say c, note that c, infinity is not a number, then y equals c is a horizontal asymptote. So we would say that number, if it's a specific number, then a constant, then that's the horizontal asymptote. So find the horizontal asymptote of this particular number. So again, we look at the highest terms, which is here and here. So we find the behavior of this negative 6x to the power 4, because they're the dominant terms. And we see that these cancel and get negative 6 over 7. So as this function, let's call it just f of x, because we're approaches negative 6 over 7 as basically as x goes to infinity. And it also approaches negative 6 over 7 as x goes to negative infinity. We see this. So therefore, this y equals negative 6 over 7 is a horizontal asymptote. And if you wish, you could use to check, this is not sponsored by Google, but use basically a graphing calculator or just use Google or Desmos to check, right? To see what this looks like. Or just Google to see the graph. And just to check where the horizontal asymptote is. Check horizontal asymptote. Like, where is it? So you could do that. It's your choice. Now moving on, exponential functions, logs, and e. So first of all, let's remember that we define the meaning of an expression a to the exponent b, where a is any real number and b is a rational number. However, we have not defined the meaning of such expressions when b is an irrational number. So remember, irrational numbers are something like this, where, like, let's say the square root of 2, square root of 3, pi, those were irrational numbers. They were some irrational number. But we want to figure out 7 to the power, let's say, square root of 2. What happens there when it's to the exponent of irrational number? So the irrational exponent, suppose b is greater than 0 and x is an irrational number, then b to the exponent x can be thought of as a number that is approximated by numbers of this form, b to the exponent r, as r takes on rational values near r. Okay, so near x. So this is the idea. You get like closer and closer to this value. So for example, square root of 2 is 1.41. Sorry. Need to erase this. .4142. I won't get into every little detail, but we get closer and closer to this value. So 7 to the exponent square root of 2, well, that's equal to, we can approximate like 7 to the exponent 1.4, and then 7 to exponent 1.41, etc. And then the next power. And continue on. So an expression of this form, b to the exponent x, that is, a variable is the power of, it's called the exponential function. So we know what to do when the power is irrational, and we already knew what to do when it was rational. So we can just list some nice properties, essentially. So we're going to be like looking at functions like f of x equals b of x. Let's say for this exponent, f of x equals 2 of x, where instead of the b, we have a 2. And so it's kind of like basically the same thing as what we've been doing before, just with irrational numbers. And we're taking approximations. You could approximate it an irrational number by a rational number. I hope I kind of convinced you. It's not the best explanation. But suppose x and b are positive numbers and x and y are real numbers. So this time, this is for everything here. And they're positive here. Then we have like these properties from before. Now, essentially, like they're allowed, in this case, to be any real numbers is the point. Any real numbers. Because before we noticed that we've already seen these identities, and we kind of derived them. X and Y had to be rational numbers, but we're now going to allow them to be irrational numbers. It's the same properties hold. So let's graph like these functions of exponential functions. Let a be a positive number. What does the graph of an exponential function of f of x equals a to the x look like? Well, it depends on what a is, essentially. So suppose like here, a is greater than 0, and x is in a set of real numbers. So we could plot this. But let's use an example first. Let's say a is equal to 2, and f of x is equal to 2x. So if we plot this, when x equals 0, 2 to the power 0 is 1. So that's our first point. This is 0, 1. And we can plot other points, like let's say 1. Well, 2 to the power 1 is 2. What about -1? Well, that would be like a half, etc. So we can plot some points. And we can see what happens as x goes to infinity. This is going to shoot up. But as x goes to -infinity, y kind of approaches 0. And here, y is approaching infinity. So it's like easy for me to draw a nice curve that you kind of curve it up, keeps going up and up and up. This goes down, kind of like that. Okay, interesting. Let's see another example. What happens when a is equal to 0.5? So therefore, our function is going to look like 0.5 to exponent x. Let's draw this function and sketch it. Draw it down here. So when it's x is 0, anything to the power 0 is 1. So this is again is 1. So we have like that point. What about, what about -1? When x is -1 here, what do we get? Well, we got 1 over 0.5, which is 2. So this will be 2. What about when 0.5, when x is -2? We get 4. So this will be up here. And we could draw more points. And then we can connect this curve. So you notice as x goes to infinity, y goes to 0. When x goes to negative infinity on this side, y is going to go to positive infinity. So these are 2 examples. I'll just finish this example. Just to summarize it. So this approaches positive infinity as x approaches positive infinity. This approaches 0 as this goes to negative infinity. If it's between 1 and a is between 1 and 0, we see that this approaches 0 as this goes to positive infinity. This approaches infinity as this goes to negative infinity. And we noticed something, that it went through this 0.01, both of the graphs. So I'll just write this out and then we'll conclude.